Hi, and welcome to Quick Maths on differentiation, also known as the gradient function. I will begin with the end in mind, which is the relationship between the polynomial function and the gradient function. When the polynomial function is y equal to the product of a x to the power of n, its gradient function, written as dy dx, is the product of a n and x to the power n minus 1. When you perform dy dx against an existing dy dx, it is also known as its second derivative, and it is the product of a n, n minus 1, and x to the power n minus 2. The second portion of this slide is merely to show what becomes of fx when its gradient function and its second derivative is expressed. By referencing the given relationship, here are some examples where when y is equals to 3x, its dy dx is 3. And when y equals 5x, its dy dx is 5. When y is equals to minus 7x, its dy dx is minus 7. And finally, when y is equal to 3x plus 8, its dy dx is 3. It is intentional that all the given examples are some form of a linear equation where its dy dx resembles m in y equals mx plus c. In graphical form, you can pick any 2 points from the graph to calculate m as being y2 minus y1 over x2 minus x1. The reason you can choose any 2 points to calculate its gradient is because all points on the graph share the same gradient. However, in a non-linear equation, its gradient is different for different points on the non-linear equation. From a mathematical perspective, this will be the gradient of the tangent to the curve at a specific point. We know that the tangent is most likely to be different as the point changes, hence supporting what is said in the first statement. In applying the relationship against a nonlinear equation, for example, y equals x cubed, its dy dx is 3x squared. For the specific point 464 on y equals x cubed, its gradient can be calculated by inserting the value of 4 to replace x for its dy dx, which comes to the product of 3 and 4 squared. This comes to 48. Second example is when y equals 5x to the power of 4, where its dy dx is 20x to the power of 3, and at the point 280 on the y graph, its gradient is 160. As a third example, when y is a cubic polynomial, the cubic polynomial will have a dy dx that's equal to 21x squared plus 4x plus 11. And at its point 133, its gradient is 36. The relationship appears straightforward, but how did we get there in the first place? Is there a way to show this by tangential method, perhaps for a specific fx? Yes, and you may be asked to work on this as a math problem. Now, for reference only, I will choose fx as being equal to 7x squared plus 11x and will apply the gradient function to get to its gradient being equal to 14x plus 11, which I can use as a validation against what I do below when we derive the solution without the standard formula. To find the gradient without the standard formula, I will need to create another point, such as to enable me to calculate its gradient using y2 minus y1 over x2 minus x1. with x1, y1 being x and the function of x, I will next make x2, y2 as x plus h and the function of x plus h, and knowing h needing to be as small as possible to get the most accurate tangent. By substituting xy, y1, x2, y2 with all the chosen values and simplify the equation, we should be able to get h limiting to 0 as being equal to 14x plus 11 plus 7h. And when h limits to 0, it becomes 14x plus 11. By observation, y2 minus y1 over x2 minus x1 can be generalized as h limiting to 0, the function of x plus h minus function of x, all being divided by h. Tutorial question 1. Differentiate the following function of x. The respective solutions are as follows. Tutorial question 2. Find the second derivatives for each of the stated functions. The required solution is like applying dy dx to its existing dy dx. Tutorial question 3. For the curve fx equals 12x to the power 4 minus 3x squared plus 7, identify its gradient at the coordinates 2, 1, 8, 7. For the question, you perform its first derivative, then insert 2 to replace the x for its first derivative. This should result to 372. And if one is asked to find the gradient of a tangent for the same curve at the same point, the working is exactly the same. Tutorial question 4. Find the coordinate where the curve fx equals 3x squared plus 1 has the gradient of 15. For the question, its first derivative is 6x. Therefore, 6x is equal to its gradient of 15, enabling us to solve for x being equal to 2.5. When x is 2.5, fx can be calculated as 19.75, which incidentally is the y-coordinate. Therefore, the required coordinate is 2.5 and 19.75. At the stationary point, its gradient is known to equal to 0. Having introduced dy dx, or the first derivative of a function, we can easily differentiate fx and equate it to 0 to solve for the x value of its stationary point. The example shows how we could identify a stationary point of a specific function using the completing the square method. From our learnings on differentiation, we have an alternative to solving the above. We could start by differentiating the function and equating it to being 0 in order to be able to solve for x, then identify y by placing this value of x into fx. I wish to repeat that at the stationary point, its gradient is equal to 0. And having being introduced to its first derivative, we can easily differentiate the function and equate it with 0 to solve for x. This is especially effective with cubic polynomials or polynomials of higher order. Additionally, it is to be noted that when the second derivative is larger than 0, the stationary point can be identified as a minimum point. And when its second derivative is less than 0, the stationary point is the maximum point. Having said so, we should be able to find the coordinate for the minimum and maximum points for a given cubic polynomial. We'll start the usual of doing its first derivative to solve for x. Then identify their respective y values, and using its second derivative to tie if each of the coordinates is a maximum or a minimum point. Tutorial question 5. Find the coordinate at which the curve fx equals 3x squared plus 1 is at its minimum, and show why the coordinate is a minimum using the second derivative. We'll start the usual of identifying its first derivative, knowing that at its stationary point its first derivative is equal to 0. We could solve for x being equal to 0 and then work out its y, which will allow us to get to the required coordinate of 0, 1. Next, we'll perform its second derivative, and knowing that this is larger than 0, the coordinate is representing a minimum. Now, let's think through what we already know. A quadratic polynomial with a positive coefficient for its x squared will take a U shape, therefore carrying a minimum. Given its simplistic form, it will intersect the y-axis at 1, which incidentally will be where its stationary point is. That's all on differentiation. If you've liked and enjoyed this video, do be on the lookout for other videos under the KT tutorial channel.